a title for the cameras. I am, yeah. Yep, so that guy there just set me up for recording. So here we go. So you remember, you sound so convincing, Roger. It's the way you hold the iPhone.
Well, you got to trust my head secretary to take good notes.
So, one thing that I told you I was going to tell you last time, but I just ran out of time for, was, if you remember, part of the step with the MPS was to take this portion of the chain and apply a time evolution gate to it. What I was going to explain was why we include these guys here. So if we're updating, say, gamma 5, lambda 5, lambda 6, gamma 6, lambda 7, why we include lambdas 5 and 7 on here. And the reason for that is as follows. If you remember that when we compute expectation values of terms in the Hamiltonian, we make use of the fact that to both sides we can just reduce everything sticking off the edge to the identity. Well, let's just have a look at how that goes now. Here's our term from the Hamiltonian. And we've made sure that to the right we've got the identity to the right, to the left we've got the identity to the left. So first of all, these two here, gamma 1, 2, 3, 4, 5 and gamma dagger, are going to simplify to the identity here. Next, over this side, we've got U and U dagger. So we've got gamma 1 and gamma 1 dagger, which we obtained from the U in a singular value decomposition. So they're going to go like that. Now, next ones, you see we've got a gamma and a lambda, and we want to be able to absorb all of these into just another identity. So that's the reason for including the lambdas in here. When we contract this all into a great big blob, then we singular value decompose it. We've got this piece which is derived from, which is unitary to the left, and this piece which is unitary to the right. What we want to do is, and then we multiply by the inverse of lambda 5 and lambda 7 on these legs here, so that we then have lambda 5 times lambda 5 inverse u is a unitary. So that's lambda 5, and that's lambda 5 inverse u. And so we combine these two back together, and we've got a unitary which satisfies so that's lambda 5 inverse u dagger. This equals the identity to that side. And we only get that because we included lambda 5, lambda 7 here, and then we multiplied by their inverses here. And so that means that this piece of the network here, again, also just reduces to the identity. And if we were to continue, if there were more sections, then again, that would repeat on every section as we went along. So that's just the explanation as to why we needed to include these when we did this, when we did the update of the network. But that's not going to be the main subject of what I'm going to talk about today. Today I'm going to introduce you to a different tensor network, which I've sketched up very briefly earlier, And that's an example of a multi-scale entanglement renormalization ansatz, or mirror.
So the what I missed last time was this DBD.
Yeah, that's right, Roger.
So this H is time evolution? This is a square block, or what is it?
Over here, it's a two-site term from the Hamiltonian, and we're calculating the energy. Here, it's a time evolution operator. Well, an imaginary time evolution operator.
Okay.
Now, so this time, it's going to be all about the multiscale entanglement renormalization ansatz. In fact, it's a class of ansätze. So there are many different mirrors. But the example I'm going to talk about is the one that we use most commonly in one dimension, the 3-into-1 mirror. So whereas the MPS had basically a one-line structure, a one-layer structure, so we say it reflects the physical geometry of the lattice.
So this is just a one-line MPS with like Hamiltonian operators applied to it? Is that the way to look at it?
Yeah, one-line MPS applying imaginary time evolution to find the ground state of a system.
Yeah, okay.
What we're going to do now is we're going to look at the mirror. And this is a tensor network with a much more complicated structure. So again, what we do is we start off with a decomposition of some general state, which we represent by this tensor C. Only this time we decompose it in a structure that looks something like this. So I'll draw an example for 18 sites. First thing we have is we have a row of tensors that we call disentanglers. These are unitary tensors. So they satisfy this relationship here. U dagger equals the identity. Then we have a row of what's called isometries, which coarse grain the original lattice. So we're going from, in this case, we're going from an 18-site lattice, we're doing a 3-into-1 coarse graining. These isometries satisfy another relationship. And we usually label these by W, which is similar to that of the disentanglers. However, being a projector from a larger space to a smaller space, we do not have, so we have that does not equal the identity like that. Basically, what the isometries do is they perform they basically are a projection from the space of 3 sites at this level into the space of 1 site on. They basically project from 3 sites down into 1, and possibly perform and in the process possibly perform a unitary transformation on the 1 site. So what we've done is we've gone from a lattice which we'll call L0, the original physical lattice, which was an 18-site lattice, to a lattice that we'll call L1.
So how do you know that this works? I mean, in real space RG, you have like a scale invariance problem.
Yeah.
You know that the entanglement renormalization preserves the correct degrees of freedom, or the essential degrees of freedom, or whatever.
Okay, it's all in your optimization process. So in your optimization process, you determine which degrees of freedom are retained for your system. And also you have the question, can it possibly preserve enough degrees of freedom and enough entanglement to demonstrate scale invariance? And I'll explain how we know that it can even for critical systems in just a moment. I actually touched on this in the first lecture, but it's something that I'm planning on just reminding about now. So we've gone from an 18-site lattice down to a 6-site lattice, a 3-into-1 coarse graining. Now we may, and then we're going to repeat the process on the coarse-grained lattice. So another isometry, so another disentangler. Two more isometries. And now we're down to a two-site lattice L2. And we're just going to exactly diagonalize on that two-site lattice to find either a ground state or we could find the low-energy subspace. If I just put a single tensor here, then this diagram, of course, if you contracted it, would give you back a state on 18 sites, and so represents a single state. If you want to represent multiple states, you can put an extra index on there which will enumerate the different states. So, which is usually labeled something like with the Greek letter of your choice, say Xi. So, in practice, we often start, we might have some fairly small value of physical dimension here, say 2, which for the mirror we tend to denote the dimension of an index by chi. On the coarse-grained lattice, we've done a 3-into-1 coarse graining. We can actually typically keep, so we could in this example keep the entire space, chi equals 8. And so in this example, this is a unitary and the isometry is also a unitary because it's transforming from a space of dimension 8, 2 times 2 times 2, to another space of dimension 8. This lets us increase the value of chi over the first few layers, but we quickly reach a sort of a limit on what we can computationally process. So 8 times 8 times 8, that's going to be a bit too large for us. 2 to the 9, 512. We can't manage that. We might truncate chi at, say, we might limit chi to, say, 12 or something like that. And there are techniques for increasing the value of chi in a running simulation, but for now we'll just assume that you're going to stick with your initial choice, say 2, 8, 12. So now these are definitely projectors. Yeah, and then you sort of go 12 to 12 to 12 to 12 to 12 on any further layers that you might have. Now, generally speaking, your mirror is going to have, to a reasonable approximation, all the bonds, all the indices, or bonds as we often tend to call them, are of equal dimension. That is, the index ranges for the range of the index is the same. So 1 to 2, 1 to 8, they'll all be the same. So call them all one. We'll assume they're all say 1 to 12 for the sake of the next argument I'm going to present. This is why mirror works for 1D critical systems. So the scaling of entanglement in a 1D critical system is, if we look at a region of that 1D critical system of length L and compute the entanglement to the rest of the system, then the entanglement scales as log L. Now, the mirror I've drawn here is finite, but I'm going to present the argument on this because I'll talk about the scaling variant mirror that we use for infinite critical systems later. But I can show you the argument now. So we want to be able to reproduce an entanglement that scales as log L in the size of a portion of the system. Now, with the MPS, you had a structure which, just leaving out, just not sketching the lambdas for brevity, you can basically represent something like this. For any length, for any portion, say a 2-site length, a 3-site length, a 4-site length, you can always cut it off from the rest of the system by breaking 2 bonds, cutting 2 indices. That is, there's a bipartition of the system into 2 parts, and we can think of this as equivalent to doing a singular value decomposition. And the maximum, and now a state represented by this MPS, the maximum rank singular value or Schmidt decomposition you can have for such a system is one that has, if this link is of dimension D1 and this link is of dimension D2, then your bipartition of the system is incapable of encoding a Schmidt rank higher than D1 times D2. And that's the same regardless of the length of regardless of this length L. So in other words, your entanglement that you can encode in an MPS is between a region of length L and the rest of the system doesn't scale with L. Now with a mirror, as you grow the system larger and larger, the number of coarse graining steps you're going to have to perform also gets larger and larger. And so the number of layers of mirror you have scales as log L. For the 3-to-1 mirror, it in fact scales as log base 3 L. And so to perform a bipartition of the system, say, for example, if we were to cut off 3 sites here, we're going to have to do something like, I should use a different color for this. We're going to have to do something like this maybe. Doesn't matter exactly what. What we do is we look for the one with the lowest rank, and that's the one that provides the, so yeah, sort of the lowest total number, lowest product of the dimensions of the legs cut. And that's what gives us our, and the lowest such value gives us the upper bound on the amount of entanglement that the network can encode. Now, if we go up to 9 sites, then the easiest way is going to be to come up here. Maybe I should have gone for 8 sites, because I've gone right out the edge of the diagram in this example. Normally, we'd have to cut, if this was a larger network, we'd have another, it would continue over in this direction, and we'd have to cut some more indices coming back down. Basically, having to code, instead of just being able to cut one index here to go from here to here, we've now had to come up another layer, cut a few more indices to get across. You find that this total dimension, the product of the dimensions of all the indices that you've cut, scales logarithmically in the size of this length L. And so you can reproduce entanglements which scales as log L. And that's why we know that that's why we suspected that the 1D mirror would be a good ansatz for critical systems.
So if you go to higher D,
higher D, the 2D mirror can capture entanglement which scales as L, which is some but not all critical systems in 2 dimensions.
L?
L, yes.
So area law?
Sorry? Yeah.
Like area law?
Yep, area law. However, there's a new development, the branching mirror, which can capture logarithmic corrections to the area law, so L log L.
L plus log L or L times log L?
L times log L. So, yeah, but that's not going to be in this talk. So now, you have your ansatz, how we break down the original tensor C. Now you need to know how we update the mirror. And this is not typically done using imaginary time evolution. The method I'm going to show you, because basically that just gets rather complicated. If you have, say, a gate across these 2 sites, for example, absorbing it into the rest of the network and its effects on all the different layers is going to be difficult to it's going to be difficult to compute how it affects the higher layers of the network. Instead, what we do is we take an approach where we say what we're actually looking to do is to minimize a cost function, for example, the expectation value of the Hamiltonian. And so what we do is we say we'll start with our initial guess as to the state. So typically either a systematically set up arbitrary initial state or random contents in all the tensors. It doesn't really matter too much because it'll converge fairly rapidly towards a better representation of the ground state. And even if the overlap's initially nil with the true ground state, as a numerical noise from your computations always introduces a bit of overlap anyway. So what you do is you start off with your initial state. I'm going to have to draw this bigger again. You start off with your initial state, and what you do is you iterate across all the tensors in it and say, I'm going to update this tensor, assuming that all the others remain constant. I'm going to find the best tensor I'm going to take this tensor out and find the best one I can put in its place to minimize the value of the expectation value of H.
Yeah, but how do you do that? Because you don't have any guidance from Hamiltonian.
You're doing this with respect. You've got some Hamiltonian. You're updating with respect to that to find the low energy subspace with respect to that Hamiltonian.
Okay, I understand you can minimize some cost function based on the energy, but how do you update the tensor? Like, just you have some.
Right. Going to show you that now. So what you do is you say, if we're going to say update this tensor here, what we do is we we remove that tensor from the network. And then we say, OK, if I'm computing the expectation value of the Hamiltonian, then I'm also going to need the var. I'll just put in, so I'll put in the Hamiltonian terms in a moment.
And the Brown and Kett are different in general?
No. The bra is obtained by, so the bra is obtained by complex conjugating. So in general, if we have a Kett represented by C, then the bra is represented by, we take the complex conjugate of the entries and we vertically reflect the tensor. So that's basically, if this is C, then this is C dagger. And where the reversing of the order of the tensors in the diagrammatic notation is equivalent to transpose for matrices. So
isn't that only diagonal matrix elements?
Hmm? Sorry? Is what only diagonal matrix element? Just a moment. I haven't put the Hamiltonian in yet here. So, yeah, going to put an operator in. Now then, we have 4 terms in the Hamiltonian, which, so, okay, first things first. There's going to be terms in the Hamiltonian which are going to, so, for example, this is one of the terms where that's the term in the Hamiltonian. This is one of the terms. So the energy is going to be a sum over all possible positions of, so if our Hamiltonian is a sum over 2 site terms, then our expectation value of the Hamiltonian is going to be a sum over diagrams like this, bra, Kett, and 2 site term. This is just one of the example terms. We're going to update this particular tensor here. So we take that one out. And the other thing we do is we observe that within this diagram, there's a lot of pairings that are going to vanish. So recalling that UU dagger equals the identity, we can take all these disentanglers here, and they'll pairwise annihilate. And now you see that this isometry annihilates with this one. So that bit of the diagram simplifies as well. This one with this one, this one with this one, this one with this one. Very simple. And then this disentangler will annihilate with this one. And this isometry with this one, all very nice. And so you see that we only actually need to deal with a fairly small part of the tensor network. That's all very well and good. Our situation is made even easier by recognizing that instead of having to work with diagrams like this, we can actually compute the reduced density matrix on this level L1, this level L2, so on levels L2, L1, L0. And the way we do that, we start off at L2, and we write we turn the top tensor into a reduced density matrix like that. So this is the top tensor here, and this is T dagger. And so we could put in So we can put in a reduced density matrix like that. Actually, I'm going to rub off a bit of this, and I'm going to, well, no, I'll leave this up for now for reference, and I'll come back to it in a moment, because there's something we can do to it, because, yeah. So, okay, TT dagger equals reduced density matrix. Now we want to work out the reduced density matrix on level 1 and on level 2. Now, what you're seeing here is that we're looking at, best way to explain this. There's an idea that possibly I could do with introducing about now, which is what we call the width of the causal cone in a mirror. So if you have an operator on two sides of a mirror, of a 3-to-1 mirror, so let's put it here for sake of argument, and you want to see which sites on level, what you can say is, if we have an operator on two sites of level 0 here, then if we were to try and construct an equivalent operator on level 1, how large would that operator be? How many sites? So if we look at this diagram over here, we've got a two-site operator on level 0. What we can do, we've annihilated everything else in this diagram. You can now see that if we now contract this region of the diagram here, we've got a two-site operator on level 1. This whole block here becomes a two-site operator on level 1. We could also have done the same with an operator on here. All three of those locations for operators contribute to a two-site operator on the same two sites in level 1. It so happens that for every two-site operator on level 1, there are contributions from 3 two-site operators on level 0. And the same with every two-site operator on level 2, there's contributions from 3 two-site operators on level 1. And it works in the opposite direction as well. So, I mean, up here, going up one further level in this example, you see that this particular location actually contracts to a one-site operator on level 2. That's nice. We could do it as a two-site operator if we wanted to, by including that leg there, and that's the more general case. In general, you can always do it as a two-site operator. It's just luck that I picked one that we could do as a one-site operator here. Now, we can also do this in the opposite direction. We can say, if I have a reduced density matrix on these two sites here, then that's a reduced density matrix which I can compute the expectation value of this two-site operator as follows. There's the white. I can compute the expectation value of, that should be, of that operator like that, which is simply trace of rho times the operator. So what that means is that that's equivalent, and that comes, this operator can be seen as a sum over 3 terms on the level below, which were the operator between these two legs of the isometry, these two sorry, in this example, I've shot myself in the foot a little by doing this on a finite mirror. Let's go to a, because in general, we're going to have disentangler here, another isometry out here, and this time we've got, so let's see. We've got suppose we've got a disentangler, suppose we've got a reduced density matrix on this level here, which is, so L0, L1, L2. We've got a reduced density matrix up here on L2. And we can compute trace of, we can take this two-site operator here. So we've got a reduced density matrix up here on L2. We've got a two-site operator constructed from 3 terms on L1. They correspond to an operator on here, these 2 sites, an operator on these 2 sites, an operator on these 2 sites. So we can write trace of, so I'll call this O2. So we can compute the expectation value of O2 by doing trace of row O2. Or we could write O2 as a sum of the 3 terms which go into it, which is an operator on these 2 sites, an operator, so that's the operator on these 2 sites, an operator on these 2 sites, and an operator on these 2 sites. So that's a sum over 3 terms. So what we see is that trace of row O2 can be written as a sum of 3 traces, and what we can either do is we can take these 3 operators, and we can do what we did here, combine them with the surrounding area of the local network to form an operator on the coarse-grained network, or we can do the opposite. We can take the reduced density matrix and combine it with those extra operators to get a reduced density matrix on the fine-grained network, so we can come back down the tree. So just to simplify, go back to the simpler example we were looking at earlier, where we had one operator here, which we can lift up to the level above. So we might have, say, if we're talking about if this is row 2, and this is one of the terms contributing to trace of row O2, then we can either lift this up to give us an operator on level 2, or we can absorb all these into the reduced density matrix to give us a reduced density matrix acting on level 1, where these 4 indices here correspond to these 4 indices here. So we can bring the reduced density matrix down the levels. So using these tricks, we can construct a reduced density matrix on any 4 sites, or we can lift it, so we can start with a reduced density matrix constructed from the top tensor and its conjugate. And then we can use that to construct reduced density matrices at all levels. So now this brings us back to, and so that lets us compute the expectation value of H as a sum over terms. Now we come back to our problem of if we're optimizing one particular tensor. If you actually look at the energy expectation sum, you see that that tensor is only involved in computing the energy expectation value for 3 terms. That's this one, and this one. So what we do is we can knock out this tensor here, and then we sum up this diagram and this diagram and this diagram, which gives us a sum over 3 operators that look like this. And so we call that the environment of U, where U is the disentangler we've just taken out. To compute the updated version of U, we want a U which maximizes the magnitude of the expectation value of the energy, because we chose our Hamiltonian, because like with imaginary time evolution, we choose our Hamiltonian to have all eigenvalues 0 or negative. So we want to maximize the magnitude of the expectation value of the energy. And the way that we do that, given an environment E, which is the sum over the 3 relevant terms, is we take the singular value decomposition of E. Well, that's a capital U as opposed to the disentanglers, which we tend to label as small u. And then we write, whoops, U prime, the new disentangler. We construct that from, that's equal to minus V U dagger. Because then we have that trace of U E dagger equals equals trace of minus V U dagger U S V dagger. And by the cyclic properties of, well, first of all, that U dagger U cancels. And by the cyclic property of the trace, that V dagger and V cancel. And so we have equals trace of minus S, which is the maximum magnitude value. So you see we're, so you see this is how we maximize expectation value of the energy. We do it.
Can you know S?
S. This is just the singular value of the environment E, and so S is a diagonal matrix, all of whose elements are positive or zero, and so to minimize the energy corresponding to maximizing the magnitude of the expectation value of H, the best you can do is to sum all the elements on the diagonal on. So to sum all the elements on the diagonal of S, and then put a minus sign in front. That's a result from linear algebra, which I'm not going to prove, but that is the best that you can do. So what we do is, site by site, we update each tensor, every tensor in the mirror. So all the U's on one level, then all the W's on the next, so on the same level. Then we move up to the next level. And do you remember I said we can take our two-site operators and combine them? So what we do is we take them in groups of 3 and we combine them into two-site operators on this level. And then we do the same process here, update all the U's, update all the W's. Then we get up to the top. We have a Hamiltonian up here that we can exactly diagonalize. We do that, we compute a new top tensor. And then we take that top tensor, and you recall that I showed you how we can take a reduced density matrix back down, that we end up with a sum over 3 diagrams like let's see, I'll put it off to one side this time just for variety. So for a specific location, we can compute a reduced density matrix like this. We can contract that with the network of tensors to get the reduced density matrix on the next level down. So we can compute one for these two sides, we can compute one for these two sides, we can compute one for these two sides. So we can come back down the network as well. In practice, we tend to simplify things a little bit and assume translation invariance. If we're working with a translation invariant Hamiltonian, we'll tend to neglect edge effects and say that all the disentanglers are equal, all the isometries are equal on a particular level.
If you went up in level, if you weren't truncating the dimension, would this procedure be exact?
Yeah. Okay. So in the limit that you don't truncate at all, it's just not a particularly quick way of doing exact diagonalization. Right. Now, if we're assuming translation invariance, then similarly we can impose that the reduced density matrix should be the same on all pairs of sites. So then your lowering of the reduced density matrix turns into a sum over 3 terms. Well, an average, actually. And the third term is like this one, only with the gaps there instead of there. So that's how you bring the reduced density matrix down, sort of on average, so with translation invariance. Now, we've got all the ingredients we need there to perform an iterative update of our mirror. We can update individual tensors. We can take the Hamiltonian up a layer and do the same on the next layer. We can do that all the way up, and we can come all the way down with the reduced. We can construct a new reduced density matrix at the top, and we can do that all the way down as well. Point worth mentioning is that you recall I showed you that being able to bring the reduced density matrix down does make life a lot simpler for us. Do we have any more white chalk?
With those last pictures, what do you mean where you copy the lines? Are they free indices? Or?
Yeah, that's free indices. So this is going to equal.
Is that the same as the one above where you inserted the extra operator?
Which one? Oh, this one up here. Yeah. Again, those here correspond to these over here, the free indices. And over here, we are calculating rho on the level below. These free indices correspond to these ones here in this diagram, these ones here in this diagram, and in the other diagram, they'd be here, 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 here. So it's like open indices correspond to open indices.
And what was the matrix you put in there?
Up here? This matrix here is a two-site term from the Hamiltonian. So, yeah, that's little h. So what we're doing here is we've taken out one tensor, and we've got, well, actually, if this was rho 1, then that would be little h. If this is rho 2, then this is going to be one of these orange operators that's got by taking little h on 3 adjacent sites and summing them together to get a little h on the next level up. So, because we can get the reduced density matrix at every level, and because we can get the Hamiltonian at every level, we can start with the reduced density matrix at the top, and we can take it down using this approach here. And because we can take a Hamiltonian at the bottom, and we can take it up using the same approach. So we use this to go from, say, a Hamiltonian on level 0 to a Hamiltonian on level 1, or from level 1 to level 2. And we use this one to go from level 1 to, for a reduced density matrix on level 2 to 1, 1 to 0. We never have to deal with a diagram much larger than these. If we want to compute the replacement for a disentangler, then we look at the set of all possible diagrams that we might need to look at, but we only need to look at one layer of the mirror, because we can use the reduced density matrix that we've got. If we're working on level, if we're working from 0 to 1, if we're optimizing a disentangler that lies between level 0 and level 1, then we only ever need to deal with 3 diagrams like that, because I'll just start at the left again. I'll just sketch the diagrams. It'll probably be fairly apparent once I've done that. Once again, we only have 3 terms that are going to be particularly relevant. Well, that are going to be relevant. our environment is made up of So we construct our environment out of 3 terms like this. These are the only 3 terms we need to consider. This is our disentangler. So this is where our disentangler was. We've got a Hamiltonian term to the left that overlaps with it, in the middle that overlaps with it, and to the right that overlaps with it. And these are the 3 terms that we have to sum up to get our environment. Pretty nice, pretty straightforward. We always leave in U dagger. We assume we only vary with respect to U, and we leave U dagger in there. That's worth mentioning. Just keeps the actual maths computationally feasible. Similarly, when we're doing the isometries, we take a look at what happens if we knock out this isometry, and we actually have 6 diagrams. We have to worry about the Hamiltonian. We have to worry about the Hamiltonian here. So if I look at the whole, one convenient way of looking at this is you look at the whole diagram with nothing removed, and you say, where could the Hamiltonian be that will affect that the tensor I'm looking at? So when you're computing the expectation value of the energy, you're looking at basically diagrams like this, with the Hamiltonian term either here, 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 or you're looking at, say, it could be here, here, here. If it's here, you're actually looking at this isometry and this isometry. So we shift it back, and that's like here on this diagram. You're looking at diagrams like these the whole time. Now, if we're updating an isometry, say updating this isometry, then the Hamiltonian here is going to be relevant because this isometry appears in diagrams including this term of the Hamiltonian. Here it's going to be relevant. Here it's going to be relevant. It's also going to be relevant when the Hamiltonian is here, corresponding to this isometry being this one here. The isometry we were looking at no longer being this one, but now being the one on the right-hand side of the diagram. So we've basically moved from looking at, say, sites 10, 11, 12, 13, 14, 15. We've moved over to sites 7, 8, 9, 10, 11, 12. So now this is the one that we've knocked out. And now for this one, we have a Hamiltonian term here, here, here. So you get 6 diagrams when you're updating the isometries. Anyway, that is how we do updates for the disentanglers, how we do updates for the isometries, how we keep all of our diagrams nice and small and feasible. We never have to work with diagrams including more than 8 tensors. Before I go on, is there any bit of that anyone would like me to recap or to clarify or to try and put in a slightly clearer order, perhaps? Okay. Now, there's a paper on arXiv which contains a detailed description of all of this process, how you update your mirror. If I remember rightly, then the one to look at is Algorithms for Entanglement Renormalization by Glenn Evenbley. And Gifrey Vidal. Okay. And that that basically explains all of this in greater detail and provides all the diagrams for computing the environments of a disentangler, environments of an isometry. The isometries, you proceed exactly the same, only your environment looks like this. And so minus v dagger u is going to typically be a rectangular matrix, which is chi cubed by chi, which corresponds, of course, to an isometry that looks like that once you reshape it. So chi cubed multiplied by chi. Okay. The next trick you can do is you can do a scale invariant mirror. And this is where you can study critical systems. So you recall that you can lift operators from one site to the next, and you can bring reduced density matrices down from one lattice to the one below. And to perform your optimizations, you only need to look at one particular level, because you've got the reduced density matrix above it, you've got the Hamiltonian, you've got the Hamiltonian on lattice L0, you've got the reduced density matrix on Li, reduced density matrix on Li plus 1, the level above, and you can use that to optimize the disentanglers and isometries in between. So all you need is a reduced density matrix, a Hamiltonian, and a layer of the mirror. What's the time? Okay, about 5 minutes then. No, that's, yeah. So all you need is that layer, the reduced density matrix above, the Hamiltonian below. In this example, what we did is we started with a mirror with a top tensor, and we used that to construct our initial reduced density matrix right at the very top. Suppose you didn't have that. Suppose your mirror goes on up forever. It's an infinitely large lattice with an infinite number of layers of mirror on top of it. What are you going to do? And the answer is actually fairly straightforward. You look at this relationship here, and you say, OK, and I'll just fill in the last diagram here quickly. And you say, by the time it gets down to, suppose we had the reduced density matrix, an infinite number of layers above us, that we knew that, and then we were able to lower that repeatedly to get to the level that we're interested in. So we're going to have applied this process essentially an infinite number of times to get our reduced density matrix. What's that reduced density matrix going to look like? Now, if we assume that, what we're going to assume is that an infinite number of layers above us, our reduced density matrix contains some portion of pretty much every. Well, okay. What we're going to say is what can survive this process. The answer is if we were to rewrite this in a slightly more general form as which I shall represent like this. We've taken an operator rho, and we've applied a super operator to it, which maps it into an operator rho prime. That super operator I've represented like this. If we apply that super operator an infinite number of times, then the only things that can survive that, we apply it an infinite number of times, what's going to happen is if our initial row contains multiple eigenoperators of this super operator, then each of those is going to get multiplied by its eigenvalue. And so the one with the ones with the largest eigenvalue are going to be the only ones that survive. Now, what we've done is we've normalized, every layer we've normalized so that our reduced density matrix always satisfies trace of the reduced density matrix equals 1. What this means is that as we apply the super operator again and again and again, we're basically projecting out all eigenvalues, so all eigenoperators of the scaling super operator, which have an eigenvalue less than 1. There aren't any with an eigenvalue more than 1, because we've kept things normalized. The reduced density matrix isn't growing. So essentially what we do is we project onto the eigenoperator of the scaling superoperator, which has eigenvalue 1. Or eigenoperators, there could be more than one of them. That's more complicated. In general, so far we've applied this to systems. We've only studied systems which have a single eigenoperator with eigenvalue 1.
Would they necessarily have eigenvalue 1, or could they have some reduced eigenvalue?
There are, in general, there's an infinite number of such operators in any critical model. In a lattice model, we're only going to realize a finite number of these. And these are going to have different eigenvalues. So there's going to be always at least one with eigenvalue 1, and then there's going to be ones with eigenvalues less than 1. Etc. And your reduced density matrix is going to consist of just this eigenoperator. And that's how you compute an initial reduced density matrix to start with. And, well, in a scale invariant system, all your layers are basically the same anyway. So that's the reduced density matrix that you care about. Similarly, you've got translation invariance, so you can assume all your isometries are the same, all your disentanglers are the same. In fact, you can represent a scale invariant mirror using just one disentangler, one isometry, and one reduced density matrix. That's pretty neat for representing an infinite critical system using a computational technique that will attack it in polynomial time. And actually, what's also nice is you can take these here, these other scaling dimensions, and you can relate those to, so you can take these other eigenvalues, and you can relate these to the scaling dimensions so you can associate a critical theory on a lattice with a conformal field theory on the continuum. You can associate local scaling operators on the critical theory with primary and secondary fields of the conformal field theory, and you can associate these eigenvalues with their scaling dimensions. And so that's a rather nice result that comes out of this, that you can calculate the scaling dimensions of the associated conformal field theory and thus identify it. I'll probably talk a bit more about the scale invariant mirror next time. I'll talk about that in a bit more detail. And that'll probably do us. I'll also have the assignment ready for next time. And yeah, I guess I'll generally take any questions. There probably won't be time to talk about internal symmetries in the mirror. That's another whole topic in its own right. But certainly that's sort of more, that's a bit more advanced anyway. This is how you do the mirror, how you do the scale invariant mirror, and that's certainly enough to get you started on simulating systems with tensor network algorithms. If you want to take it further, we've been gradually working on producing relatively didactic papers on more advanced topics like internal symmetries. It's just this initial step that tends to be a bit of a leap for getting started. So, yeah, all done. And any more questions? Any questions at all? Okay, we'll call that part 3. Thanks, guys.